The periodic table of elements is a table occupied by elements in the form of notation or symbol of the atoms of the elements and the number of proton or atomic number and the mass number or nucleon number. In this table, the elements are arranged based on the atomic number and the similar properties of the elements. The historical development of the periodic table of elements. In this section, we will discuss the history of the classification of elements, starting from the simplest one, which is based on the common physical properties, to a more complex one, which is based on the increase of atomic mass and similar physical and chemical properties. The first is Arabian and Persian chemists. Arabian and Persian chemists initially classified elements based on common physical properties, which is metal and non-metal properties. For metal properties, shiny, solid at room temperature pressure, malleable, conduct heat and electrical energy easily. For non-metal properties, dull, solid, liquid, or gas at room temperature pressure, brittle, poor conductor of heat and electricity. Antoine Lavoisier, 1789, grouped substances that he believed to be elements into gas, non-metals, metals, and earth. John Dalton classified substances in the form of elements, 36 elements at that time, based on the increase of atomic mass. The atomic mass he was referring to was the ratio of atomic mass of the element to the atomic mass of hydrogen. John Jacob Berzelius, 1828. Berzelius made improvement to Dalton grouping of elements. The more systematic periodic table starting from the Brenner's triad, proposed in 1829. Johann de Brenner grouped elements based on similar properties in group of three called as triads. For example, a triad of lithium, sodium, and potassium, Li, Na, and K, consisting of lithium, sodium, and potassium, which have similar properties, and the mass of the middle element is the average of that of before and after element. Properties: appearance, a shiny but soft metal for these three metals from lithium, sodium, and potassium. Then the melting point relatively low for metals. Boiling point relatively low for metals. Density low, thus these three metals float on water. Reactivity very reactive. These metals react vigorously with water and then react with oxygen in ratio 2:1. According to de Brenner, the mass of the middle of the element, in this example is sodium, is the average of the mass of the lithium that is listed before sodium and mass of potassium that is listed after sodium. So here the mass of sodium is mass of lithium 7 plus mass of potassium or K 39 divided by 2 equals 23. So the mass of sodium is 23. The second one is octave law proposed by Newlands in 1865. John Newland classified elements based on the increasing atomic masses and repeated trend of properties similar to the octave of music. The eighth element will repeat the properties of the first. The third is Mayer's periodic table, 1864. From the previous table, it is clear that he did not only order the elements with increasing atomic weights, but also group them according to their valencies. For example, here, for a 4 here is a valency of the carbon, silicon, stannum or tin, and lead. And then a valency 3 for a nitrogen, phosphor, astatine, stibbium, and bismuth, and so forth. The fourth, this is the base of the modern periodic table that we use today, Mendeleev periodic system or Mendeleev periodic table. Mendeleev is a Russian chemist. The name is Dmitry Mendeleev. Published the first recognizable periodic table in 1869, developed mainly to illustrate periodic trends of the then known elements. He also predicted some properties of unidentified elements that were expected to fill gaps within the table. Most of his forecasts proved to be correct. For example, here, Eka aluminium is gallium. This is the prediction that at that time had not invented yet. Then Eka boron is scandium, Eka silicon is germanium, Ge, Eka manganese is technetium, 3 manganese is rhenium, 3 tellurium is polonium, and so forth. This is there is empty at the time, had not been discovered at the time. Eka silicon is the element that predict or forecast by Mendeleev at that time, but the element had not been discovered at that time. Then after that, the germanium aluminum was invented. Then the properties almost similar. The atomic mass around 72, density around 50 point something, melting point high, color the same, gray. Oxide is refractory dioxide, density 4.7, basic, and then boiling point under 100, and germanium 86. So the prediction is correct. Chloride density 1.9, 1.9. The today periodic table we use is the modern periodic table based on the Mendeleev. Almost the same, the form or the shape. Here we have column, that is group, and then here we have a row. Row is a period, so we have 7 period. This is hydrogen and helium in period 1, row 1. Row 2, lithium beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. That's a period 2. Until this is period 3, sodium, magnesium, and so forth. So here, the last is period 7. For group, the purple one, this is group 1. The brown, this is group 2. You have the number in here, that's the number of group. That's the new way to name the group. The old way is group 1 we call as 1A, group 2 as 2A, and then from 3 until 12 that transition metals, or block D elements, and then 13 is 3A, 14 4A, 15 5A, 16 6A, 17 7A, and here is 18, that's 8A. This one is 8A. So you have here how many groups? Group 1 or 1A is alkali metals, and then group 2 is earth alkaline metals, and then you have group 3 until group 3A until group 8A. This is the main group. So group 1A, 2A, 3A until 8A, or 1, 2, 13, 14, 15, 16, 17, and 18, that's the main group. And then from group 3 until 12, that's the transition group. So here we have main group, group 1, 2, and then 13 until 18. Yeah. For group 17, the name is halogen. 17 is halogen. And 18 is noble gases. Noble gases. For transition group, divided into 2. The first is outer transition group, and then the second is inner transition group. The inner transition group, there are 2 series. Lanthanide series, this one, the green line here, and then actinide is the orange. The position of the lanthanide, the green, is in this behind lanthanide element here. Lanthanum 57, that's the name of element. So here the elements are ordered, arranged based on the atomic number. You notice here barium is 56, and then you have lanthanum 57, but after lanthanum then jump into 72 hafnium. So there is gap in here from 57 to 72. Actually, these are the elements of lanthanide, 58 until 71, lutetium, cerium until lutetium. So the position of lanthanide inside or behind the lanthanum in here. So this series of lanthanide is inside the group 3. For actinide series, the yellow, you notice here actinium, the number is 89 actinium, Actinium is the name of element. And then after 89, and then jump to rutherfordium with proton number 104. So there is gap in here. The elements in here is actinide, starting from thorium number 90 until lawrencium number 103. 103. So we have here inner transition in group 3, period 7, behind element actinium, proton number 89, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 here in here, 14 elements behind actinium.